Okay, in this video today, I'm going to be going through um, the 2018 O-level paper, which is done by Joshua. So, um, yeah, without further ado, let's start. But before I begin, I have a few things to say, right? So, firstly, you should try this paper before you watch this. And secondly, this paper is in 2018. So there's going to be a few stuff that is out of syllabus. So, but it should be fine. Most of the things will probably be useful to you. Okay, let's start. Oh, and there's no answer key, right? So I'm just gonna be seeing whether he's right based on my own brain. Okay, so let's begin. Okay, state the value of the resistor. So brown, black, orange. Bro, there's no. Oh my days. Okay, I'm just gonna assume he's right. Okay, I'm not gonna go through how to do this cause I really not. Oh, state the value of the resistor 21K is wrong actually because you need to say ohms, so you don't get any marks for this. You have to say the value of the resistor is 221K ohms, and then you can add this bit if you want. Personally, I will add this. Yeah. Okay, so then you can say 21K or 21000 times not times, plus minus 5% ohms. So that is yeah. Figure 1.2 shows an LED circuit. Um, The LED has a voltage drop of 2.1 across it and a maximum working current of 35 milliamps. Calculate the value of the resistor required to protect the LED. Okay. So let me get my calculator. Yeah, I need to verify his calculations. So okay, so first he does 7 minus 2.1 because the voltage drop across here is 2.1 volts, right? So then this would what am I doing? So using KVL, then we know what voltage is here, which would be 7 minus 2.1. So he does that, and then he finds 4.9. So here's 4.9 volts. Then we're trying to find the value of the resistor, right? We know V and we know the current because the maximum working current of the LED is 35 milliamps. So we want to keep the current to 35 milliamps and current in a series circuit is the same, right? So the current for the resistor is also going to be 35 milliamps. So with that, right, all we need to do is R equals to VI. Then we just plug in the value. So 4.9 divided by 35 milliamps. Don't forget to convert the prefix, right? So wait, hold on. Bro, this calculator sucks, bro. Whoever uses a sharp calculator is an op, bro. Give me a second. Bro, Casio calculators are the best, man. I don't know why. I don't know why sharp users. I don't know why sharp users choose to be the way they are. Okay. So 4.9 divided by 35 milliamps, which is 35 times 10 to the power negative 3, and then you get 140 ohms. So this is correct. Select two resistors from the E24 preferred resistor series that when used together would give the correct resistance that you calculated. So 75 and 75. So if you add them together, you get 140. You get 150. Okay, so we want to get something plus something is equals to 1.4 on this sheet basically. Not 1.4, like 140. Or ish, okay? Okay, we're looking for two numbers that add up to 14 here. So he did 7.5 plus, he did 75 plus 75, which is basically on this list 7.5 plus 7.5. But is there another two numbers that can add up to get exactly 140? That's my question now, basically. Okay, this might take a while. Oh, I'm close. Wait, I got 4.7 plus 9.1 is 13.8. What's after 4.7? 5.1. Oh, that's too much, I think. Yeah, that's too much. You can only get so close. But you can get closer to the number than 150. So this is wrong already, because I already have two values that can add up to be equals to a number that's very, very close. Okay, what did I have? I had um basically I have 47 ohms plus 91 ohms is equals to 138 ohms. I also have uh, 5.1, which is 51 ohms plus 91 ohms is 14.2. Okay, I'm not really gonna look too deep if there's actually two numbers that add to 140, but basically these two are probably the closest, and these two add up to 150. So therefore this is not the closest, therefore you're wrong. So yeah, okay, let's move on. Figure 2.1 shows the symbol of a BJT. State the name of each state the name of each leg of the BJT. So this is the base, this is the collector, this is the emitter. Yes. Yeah, the emitter is always, hold on. Yeah, the arrow is always on the emitter. So just remember that, then you'll know. Figure 2.1 shows two BJTs, each connected to an LED output. Okay, there's one PNP, and then there's one NPN here. Complete both circuits so that the LEDs will light up when the switch is closed. So for PNP, you need to know how the current flows. So the current actually flows like this, and then it goes in like this. From what I see here, um, when the switch is open, nothing. There's just like floating point. When you close the switch, however, this will go like this because this current is going to be stronger than this. So this is bad, this is wrong. So basically, right, you need to make it such that when the switch is closed, the current can flow to ground. And in this case, when the switch is closed, the current will be opposed by the source. So for this, right, what you have to do is, okay, firstly identify that as a PNP. Then you have to know how the current flows. Then the correct way to draw this would be definitely connect this to ground or 0 volts. Oh, and then there's the LED here or whatever. But when it's open, um, I think nothing. This is good enough actually. You don't need to. I don't think you need to cover the fact that this is a floating point value, because like I mean, if even if you like connect it to high, it doesn't make sense. There's no point. So this should be good enough actually. Okay, then for this, would okay the LED will light up when the switch is closed. So in here, when it's open, so okay, I think you're misunderstanding how to use pull up and pull down, because this is not how it works. When the switch is open, nothing is connected to it, so it's still floating. And then when the switch is closed, the current will have a choice to either go here or here. Here is lower resistance, therefore it will go here, it won't go here. So this is wrong too. The correct way will, if you want to do a pull up pull down, you can probably do uh the resistor here, then the switch is here, right? But then you can, and then there's a resistor here. If you don't do pull down, you can add another resistor here lah to ground. So then this resistance has to be higher than this resistance. So when the switch closes, right, it will rather go here than here. And when the switch is open, it will go here. This bit will be grounded. Okay, but the reason why I'm talking very hastily about this part, because it's not really the solution. I don't think you need in here to draw a pull up pull down. Otherwise they will have configured the circuit differently. So in this case, it's very It's very simple. All you have to do is just connect this to this. That was it. But once you draw this wire, it's wrong already. Okay, let's move on. Figure 2.3 shows a transistor circuit that switches on a relay operating a 230 volt motor. The relay coil consumes 450 milliwatts of power, and the transistor has a current gain of 40. Calculate the minimum current needed at X to switch on the relay. Okay, so what do you do? I have no idea what this is. Power divided by volts. Power is VI, then you divide by the supply voltage, so you get I. Okay, so you're finding the current that is flowing through the relay lah. Then with that, the current flowing through the relay is actually the current at the collector. Now they're asking for the current at X, right? This is the base. And how do these currents relate to each other? They relate by the DC current gain is equals to IC over IB. So you know this, because this is already given. You sub in those values and you get IB. So let me just make sure that all your calculations are correct. Your what? Oh yeah, this is 50 milliamps. Okay. Then 40 is equals to 50 milliamps divided by IB. So IB would be 50 milliamps divided by 40. And then you get, yeah, this. If they are strict, they are not going to accept this. The reason why is because, right, this is like doing maths. Um, you should at least write out the formulas first. So you should write, oh, PV is equals to I or whatever. But now all you're giving me is you're just putting it there. So I don't really like the presentation, but you're right. So I can't, or I think I'll be lenient this time. So please just write the formulas first, like write this or whatever before you continue on with your calculation. Okay. Figure 3.1 shows part of a circuit for a handheld electronic game. Draw a component symbol connecting A and B in the circuit that will prevent damage to the sensitive electronics if the batteries are inserted wrong. Okay, if the batteries are inserted the wrong way around, this immediately means polarity. And polarity should immediately make you think about diodes. So the diode, yeah, correct. So positive is here, so that means they want the current to be flowing like this normally. That's why your diode is facing like this, because in this configuration, it allows current to flow this way. Yeah, okay. State how the component you have drawn prevents damage if the batteries are inserted the wrong way around. The diode prevents the backflow of current in the circuit, and this protects the sensitive game electronics. I don't know. Okay, my standard for marking this is going to be a lot higher because the person who did this is actually not bad, I think, in electronics. So I'm going to mark this wrong. The reason why I'm marking this wrong is because you're going to have to state some keywords for the diode. I see here you say prevents the backflow of current. This is good. In O-level, they will probably accept this. However, again, I'm going to be very strict here. When you see diode, right, you should reference keywords like forward bias, reverse bias. So how I would have answered this question is I would say when the battery is put in the correct way, the diode would be in forward bias and allows current to go to the sensitive game electronics. When the battery is put in the wrong way, the diode would be in reverse bias and not allow current to flow to the game electronics. And this will protect the game electronics. So I've done it that way. Okay, you know what? I'll just give you the mark. That's fine. But it would be better if you said it that way. Okay. Alright, let's move on. Figure 4.1 shows a signal trace of two power supplies. Give the name of the two types of power supplies shown in figure. Bro, this is the current type, bro. This is not the type of power supply. Power supply means like batteries, means like function generator. So this is wrong. For A, you pretty much only can say function generator. Okay. For B, you can either say like batteries. You can say batteries or you can say power supply. Okay. The voltage supply in A can be converted into the voltage supply shown in B using a full wave bridge rectifier. Complete figure 4.2 showing 4 suitable components. Yeah, the diamond of diodes. So 4 marks. An AC power supply has a frequency of 20 Hz. Calculate the time period for this power supply. Why is it suddenly now you know to write the equation? Okay, anyway. So the time period, yeah, you need to know that F is the frequency is equals to 1 divided by the period. So again, you just put in the values and then you should get it. So let's see if you got it. 20 Hertz is equals to 1 divided by T. So it'll be 1 divided by 20, yeah. So 0. Yeah, this is right. Okay. Question 5. Table 5.1 shows 3 number systems. Complete 5.1 to show the decimal value of 43 written in the other systems. Okay, so for decimal to binary, what you can do is you can take 3 times. How do you convert? Oh, you can do the thing where you divide by 2. If you divide by 2, 43 divided by 2, you get oh crap. You get 2.15. Wait, what's the remainder for this? Okay, I'm just gonna waste everybody's time. I'm gonna do this the long way. So this would be 4, 3. Oh, you get a remainder of 1. So you get a remainder of 1 for 43 divided by 2, and then we get 21. 21 divided by 2 is probably 1 again. Then 10.5, which is what we get, divided by 2, is you probably get. Bro, I'm not doing this, okay? So what you can do is you can use the calculator method, okay? So I'm just going to do that now. I'm not going to explain how to do that because I already have a video. Okay, not I have a video. Ryan made a video for me on that. Okay, anyway, the answer is 101011, so this is correct. BCD, for BCD, what you're going to do, right, is you're going to split this up into separate digits. And then what is this in binary? 3 is 11 in binary, 4 is 100 in binary. But then BCD, right, each BCD number is 4 bits long, so you have to add the extra zeros to make it 4 bits. So this is probably right. Yeah, this is right. Okay. Complete table 5.2 to show the 7-segment display and BCD code for each value. So 5 BCD code. Yeah, this is just literally 5. Then 60110. Yeah. Oh, and okay. Yeah, this is 6. Yeah. Okay, this is right. Okay. Complete table 6.1. This is a NOR gate, so this is right. NOR gate. And then NOT gate. Okay, I don't know. So A bar and then this. Okay. Okay, it shows the SR latch and a truth table. Complete the truth table showing the correct sequence of outputs. Okay, whenever R for SR latches whenever reset is high, then Q will be low. Whenever S is high, Q will be high. And if you just remember that, right, you can do all these questions already. So when you set Q is high, and then when both are nothing is the safe state, and then when R is high, then Q is 0. Then Q bar is literally just the inverse of Q. So this is alright. State the type of capacitor represented by the symbol in here. The type of capacitor, yeah, polarized capacitor is good. I just thought of a misunderstanding. I think I don't think anyone is going to say electrolytic capacitor, but I don't think electrolytic capacitor is actually right, because nothing. I'm just gonna move on. It's fine. No one's gonna get this anyway. So okay, figure 7.2 shows a partially drawn capacitor. Draw 2 features on 7.1 that allow the component to be identified, to be correctly connected. So one, you show me the 2 legs, and then you show me this. I will give you the mark here, but on polarized capacitors there is no plus. There's only minus. There's a very very long bar. Like the entire thing is black, right? Then there's one long white bar with like minus signs. Okay, so, but I'll give you the mark here. So let's move on. Question 8, I think, shows a transistor circuit with a resistor capacitor circuit input. Okay, yeah, this is our syllabus. Using the formula T is equals to RC, calculate the time delay generated by the circuit when switch S1 is closed. So when S1 is closed, right, this is a RC circuit as you can see here. So RC, tau is equals to RC. So 27k ohms times 2200 picofarads. So if you do the math, if he did the math right, then he's right lah. Can I please suggest for you, when you write this, show me your conversion of the prefix. It shows that it's good if you do that. Okay. Pico is what 9 Deci centi milli deci centi milli micro nano. Oh, it's 12. Okay. So you get, oh, it's times. Oh yeah, it is times. Bro, I got 0.0000594, bro. Hold on, give me a second. Let me fix up my syntax. Yeah, I'm getting 0.0000594 seconds, which is not this. Hold on. Yeah, why did you write 59.4? So basically what I did in the calculator is I took 27000 times 2200 times 10 to the power of, oh, it's micro. Oh, it's not pico, it's micro. Oh, my bad, bro. Yeah, you got the answer. Yep. Okay. State what happens when switch S2 is closed momentarily. The capacitor will act as a power supply for the circuit as well as it will be discharging. That's not true. In fact, the opposite happens. When you close this, the capacitor will start discharging, of course, but the charge or the current of the capacitor that is discharging is not going to go anywhere else. It's not going to go anywhere else because every other path has a higher resistance than to just discharging to itself. So this is not going to happen. The correct thing to say is that also you can't really say that it acts as a power supply. Technically it does, right? But this is not the keyword that the markers are looking for. What the markers are looking for is you say when the switch is closed, the capacitor is shorted to itself and starts discharging. That's all you have to say. Okay, so the capacitor is shorted to itself and it starts discharging. State the function of component R1. The resistor is used to limit the current flowing through the base of the NPN BJT, which in turn controls the output of the BJT. This part is not really necessary. The resistor is used to limit the current flowing through the base. That is correct. You'll get the mark here, but I would have preferred if you told me what's the point of limiting the current. So the point of limiting the current, right, is to ensure that not too much current flows into the base, and then if too much current flows into the base, the BJT will get spoiled. So the reason is for protection. They didn't ask you to do it, but it would have been nice if you did. So so you get the mark, yeah. Okay, and section A is done. So I'm gonna tally up your marks, and then let's see how much you get. Section A is gonna be out of 40. So let's see. 3 plus 3 plus 2 plus 2 plus 4 plus 1 plus 2 plus 2 plus 4 plus 3 plus 1 plus 2 plus 1 plus 1. Okay, 31, that's not bad. 31 out of 40 is not bad. Okay, so let's move on to section B. Alright. The astable circuit shown in figure 9.1 is used to generate a sound as part of a shop display alarm. Okay. Figure 9.2 shows the pin connection diagram of a right timer. State the components in figure 9.1 that create the time delays in the astable signal. Yeah, it's polarized capacitor. Wait. The time delays. Bro. What? No. Yo, it's not. It's these two resistors and this capacitor. It's not this or this. Okay, you get 1 mark. Okay, I'm going to explain why it is not this and this. The point of this capacitor is to control the threshold of the trigger and the threshold pins. Basically, the threshold, right, will do something, I think, when the pin, the value at there is 2/3 the applied voltage. The trigger is going to short the capacitor or drain the capacitor when it's 1/3 voltage. this capacitor controls these values. Okay, so technically it does not, okay, but it doesn't create a time delay. This does not create a time delay. It controls when the stuff is going to happen. So it's not this. And it's not this. Do you know what this is? This is out of syllabus, by the way. This is called a coupling capacitor. The point of the coupling capacitor is to make it such that DC cannot go through. Okay, how this works is you need to understand a core principle of capacitors. When a capacitor is fully charged, it acts like an open switch. So if DC is going through this dude, it will get charged eventually, right? Once it gets charged fully, then it's going to act as an open switch. But if AC was going through, it will keep charging, discharging, charging, discharging. It will never reach full charge, and that allows the current to flow to the loudspeaker. Yeah, and we don't want DC to go to loudspeaker because DC, okay, it may not spoil it, but the only way the loudspeaker can function is for there to be AC, because that's how it works. Okay, I'm not gonna get into that. I've already said a lot about stuff that's not even tested. So it's not this capacitor either. This does not create a delay. It's these two resistors, this capacitor. And then you should have also stated their names. So they actually have names. So R1, R2, C1. And then you can say like resistor, you can state the value even if you want. But yeah. Calculate the frequency of the sound coming out of the loudspeaker. So oh, you use the wrong equation, bro. This equation that finds period is for monostable. This is astable. So this is the wrong equation. Bro. Wow, no one cares about electronics. No one cares about electronics. Damn. Okay, yeah, so basically this entire thing is wrong. It's not this, I think. Okay, wait. Okay, I'm doing this because I actually forgot the equation. Hold on. To find, and then this will check if I'm actually what I'm saying is wrong. Oh crap. What's going on? I'm pressing enter but it's not sending. Okay, there we go. What did I say? Wait, what do you write? Yeah. The period is not, yeah, it's not this. That's for monostable, exactly. So, yeah, for the period, it's different. Yeah, so what resistor did you use for this? How did you... Bro, I can't even... Okay. So you did one... What is this? 110? What does that even mean? What's this? Oh, it can't be like a 10 with a hat. That doesn't make sense. I don't get it. Plus half minus 1. Oh, you got the effective resistance. Oh man, bro. Okay. So yeah, it's okay. So apparently you need to get T high and T low to get the entire thing. So Wait, no, it's an equation that combines both of them, what? Okay, basically, use the equation that gets the, Oh, bro did this? No way! Oh, that is a major misconception, bro. Bro, just, you saw every single capacitor, right? And then you just added everything up, lah. Oh, that's tough, bro. Okay, so basically, there's an equation to get the period of a astable, right? It's in the formula sheet, so I didn't bother to memorize it. But use that. Then after that, the frequency will be 1 divided by that. Then you'll get the answer. So this is wrong. It was felt that an intermittent on and off sound was more noticeable than a continuous output. Modified circuit is tested on simulation software. Astable B now pulses astable A at a lower frequency. This is connected to the power. Oh, that's a terrible design. That's a terrible design. On the signal traces, figure 9.4, draw the signals you would expect to see on the two oscilloscopes. This and this. Okay, so let's say this is one. Then you do this. Okay, so for this you need to know whether this period is slower than this period, or this period is smaller than this period. Just agak-agak looking is this period is probably smaller, so that's why this will happen. But this is wrong. You only get 1 mark. The reason why is that in here, in this can only operate when this is high. You see this? So when the XSC1 or the output of the first 555 timer is high, only then can the bottom one be on and have a trace. And as you can see, that's not the case because you have power on here, you have power on here. Okay. Basically for this, you have to, because they relate to each other, you have to draw, literally you have to draw a dotted line to show that, oh, when this is on only, this will be on. Then during here, there's a period of nothing. You have to show me that. Otherwise, I can mark you down just like that. Okay. So, yeah, so nothing, yeah. The product to be protected in the shop is placed on top of a display surface as shown. Bro, what's up with this freaking PDF, bro? A push to break switch becomes closed when the product is lifted. Okay. The switches on the table, this switches on the astable circuit. State another suitable sensing component that will provide the same function. Um, I guess this works, but it looks like they're looking for something else. But I'm not sure. Okay, anyway. Describe how your new component would recognize when the product is lifted from the surface. The IR diode releases a beam that gets detected by the IR sensor. Oh, wait. IR sensor is not a component. IR sensor is not a component. What you're looking for is photodiode. IR sensor is not a component. So IR sensor probably means a circuit. That means this is wrong. The IR diode releases a beam that gets detected by the IR sensor when the product is removed and the beam won't be detected while the product is blocking the way. So what? Oh wait, actually no, yeah. Okay, I'll give you the mark for this lah. But this is definitely wrong because they're asking for a singular component. The thing is, I'm not too sure what it could be though. What other components are there? LDR, light dependent resistor. When the display, okay, no, that doesn't make sense either. Wait, if it's a, oh, display surface. So is this box opaque? Yeah, if this box is opaque, then this makes sense. I guess LDR can work also, maybe. You can say like the LDR, when the box is lifted, right, light can actually go there, and then it changes the resistance, voltage divider, voltage comparator, all that crap. But this question is kind of weird. I'm not too sure what the actual answer is. So, to latch the output part of the circuit, a NOR gate SR latch was added, as shown. Figure 9.6 Show how a PT push to break switch and a resistor can be connected to produce a logic 1. Okay, so when the switch is normally closed, and the switch is normally closed, what happens is, wait, won't the current just flow through? Wait, what? This is definitely wrong. This is definitely wrong. Okay. Okay, when the switch is normally closed, the current will go through this resistor, right? Then it will have the choice to go from here to here, here, or here. Because here, the resistance is higher, it won't go here. So it's going to go down, do the same thing here, go down, and then just ground itself. So this is wrong already. Okay, wait, let me turn on the lights in my room. Give me a second. Okay, so yeah, this is wrong for sure. Basically, what we want is when, and I'm just gonna do it normally now. What we want is when the switch is open, the value here is 1 or high. This color sucks. So we want 1 or high basically. Um, so with this configuration, okay, let's say in the end we configure the button and this normally closed switch, or the push to break, like this. Then we have our SR latch. Okay, I'm just gonna represent it as a box. Then they give us X. Oh wait, they're asking for this. Wait, how can be connected to produce a logic signal X when the product is lifted? Okay, so when the product is lifted, this should be 1. But when the product is lifted, then the button is open. Oh, and then it does do that. Wait, it does do that. And then when it's closed, oh, so this is right. This is right. Okay, cool. For the circuit to function correctly, the user needs to be able to replace the object on the display surface and reset. Okay. Add suitable components. Okay, GG's. So, okay, that means when the switch closes back, you need to reset everything. Um, yeah, this doesn't work because, wait, let me just erase my crap. How do I? Okay, I don't want to erase what you drew. Okay. Okay, I can see the thinking behind this because once you close this, right? Once you close this, oh, okay, for this, right? You need to identify which pin or which leg here is set, which leg is reset. Okay. So from this, okay, you can probably use context for this, this is probably set. The reason why is because we want when the product is lifted, that means when the switch is open, for this to be 1. So this is probably set because when it's 1, then it will probably send a signal to Q and then do something here. Oh, for SR latches, right? If your one side leg is set, the other side will be Q bar. So this is reset, other side is Q. Okay, now so now when basically what we want is once we close the switch, we want the SR latch to reset. Uh oh, wait. For the circuit to function, no. Okay, that means we need a separate switch, I think, because they say add suitable components, so they want us to add more crap. For this, yeah, we're probably not gonna connect it back to this normal switch. We are probably going to add a different switch to reset everything. So wait. Are you even right for this? Hold on. When, oh, you are right. Okay, yeah. Okay. So what I'm gonna design for this, So I'll probably add a switch, and then I'm gonna make it such that when the switch closes, the reset pin will be 1. So for this, I can do like a switch, right? Then I can connect this at a resistor, and then that's it. So when this switch is open, this pin will normally be 0. But once this switch closes, this will be 1, and then it resets everything. So yeah. Alright, wait, how many marks is this? 2. Okay, 2 marks. To control the temperature in a greenhouse, an electric roof vent is being developed as shown. Okay. Part of the circuit using an NTC thermistor. So draw a line. Okay, I'll accept this, right? But the fact that there's a curvature on top, right, is kind of wrong already. Because this is not valid. So it would have been better if you did this, but better if you did this, such that nothing is overlapping, because this is wrong already. But I'll give you the mark anyway. Okay. 10.3 shows a comparator that uses the thermistor as part of a potential divider, which is just a voltage divider. Calculate the voltage at A when the resistance of the resistance measures 90 kilo ohms. Okay, so yeah, it would be, and then okay, so it will be 100, because we want A, right? The voltage of A is going to be this, and this is also the voltage of this. Therefore, this is the subject. So okay, include your units, bro. Include your units. Yeah, they might not give you the mark because you didn't include units in your preliminary steps. So 100 kilo ohms divided by 190. 190. Oh yeah, yeah, yeah. Oh, bro, you can't just say this. You have to say 10. You have to say 90 plus 100. But I'll still give you the mark anyway. Okay, just be careful when you're writing your calculations. So if okay, basically this is just a normal voltage. Bro, thunder, bro. Okay, so this is just a normal voltage divider circuit equation. So yeah, you got it. You got it. Okay. There has to be a reason why it's 3 marks, because it's just putting in a calculator, and then this is actually probably enough, but it's 3 marks. So what they want to see is this. They want to see you subbing in the values individually, then you do your calculation. That's what they want. That's why it's 3 marks. Otherwise, this is like easy. Okay. The voltage comparator requires a reference voltage at pin 3. Add components to give a reference voltage of 4.5. Yeah, okay. So 4.5 is 4.5 is half of 9 volts. So we can just use 2 resistors of the same resistance to divide it evenly into 2 parts, the voltage in 2 parts. So this would be 4.5 volts. So yeah, this is correct. State the name, and include the values, yeah. State the name of a component that can be used to allow adjustments to be made to the reference voltage so that a different temperature can be set. Yeah, potentiometer. The voltage comparator has 2 inputs, pin 2 plus and pin 3 minus. Give the full name of each input. I don't even know this, bro. Non-inverting input, inverting input. Okay, you learn something every day. Explain how the voltages at pin 2 and 3 in this figure cause the output pin 7 to go high. When the voltage at the pin 2 is above the voltage in pin 3, don't say above, say it when it's higher, when it's greater. When the voltage at pin 2 is greater than the voltage at pin 3, it will produce a high output that will be pulled up by the VCC, causing output 7 to be high as well. Why will it be pulled up? Where does it say here that it will be pulled up? Because there's no pull up resistor here. So how do you know? Also for voltage comparators, okay, there's no built-in pull up resistor. So you can't say this. When the voltage at pin 2 is above or when it's greater than the voltage pin, it'll produce a higher, yeah. Yep. Cause the output pins tend to go high. I'll give you 1 mark. The voltage comparator LM311 is housed in an 8-pin DIL package. Circle pin 7. Okay, this notch represents the direction. Usually the notch is like this, and then usually this will be pin 0. So now this is pin 0. 0, 1, 2, 3, wrap around, 4, 5, 6. Sorry, not 0, 1. So 1, 2, 3, 4, 5, 6, 7, yeah, 7. So this is right. 10.6 shows the full circuit of the greenhouse ventilation system that uses a solenoid to mechanically open the vent. Give the name of the arrangement of transistors. Yeah, this is a Darlington pair. Explain, giving 2 reasons why the output signal from the comparator cannot be used to directly drive the solenoid. The current provided, the current supplied, I guess, or the output current, but I guess provided is okay, I guess, but I don't know. The current provided will be too low, and it may cause other components to have a higher load if voltage was increased to provide more current. This is okay, but this is kind of redundant. This is saying that you are suggesting to increase the voltage to make the current higher, but then it goes back to the fact that the current provided will be too low. So that doesn't really make that, so technically you're not stating a different point. So you only get 1 point. What's the other point? The current provided is not high enough. Yes, that's true. But what else? Honestly, guys, I have no idea. Yeah, I have no idea. So, yeah, okay. Alright, I'm gonna drink water. Alright, 11A, figure 11.1 shows a system diagram for an automated closed circuit television controller, I think, circuit used to monitor and record animals in the forest. During the day, the light sensor keeps the video camera working continuously. Light sensor, okay. At night, the camera only works for 10 seconds at a time when the movement sensor is activated by an animal. And then they give you the subsystem. The light sensing circuit generates an analog signal which is converted into a digital signal for the OR gate. On the graphs, draw an analog and a digital signal. Yeah, okay. I'll give you the mark. 11.3 shows a circuit for a light sensor. Component Y is known as a pull-down resistor. Explain the purpose of a pull-down resistor when sending a signal into a digital component. The pull-down resistor causes the current to flow through to the digital component instead of ground, no, that's not it. That's not it at all. So the purpose is to ensure that there's no floating value. Okay, so that means now if there was no resistor, the basically the output is either high current or nothing. And when I mean nothing, I don't mean 0 volts or logic 0. I mean we don't know. It's either high voltage or not. It's either high current or not. But that or not, we don't know. When we use a pull down resistor, we are making it such that it is only high current or 0 volts. Why does this work? You can watch my video on pull up, pull down resistors to find out more. So you need to state that the point of the pull down resistor is to make it such that the floating to make it such that the only possible inputs of the OR gate is either logic 1 or logic 0, which removes the floating value. As such, there will only be a pure logic 1 and logic 0 signal sent to the OR gate, such that logic operations can be done with maximum accuracy. That's the 2-point genius state. One is it removes the floating value, and it only produces logic 1 and logic 0, and then the point. So what? Why do I need to care if logic 1, logic 0 is being sent, or logic 1 and whatever rubbish? There's a reason, and it's to ensure the maximum accuracy of operation in the OR gate. Okay. Alright. 5 timer. Using the formula this, cause yeah, and then this calculate the value of R1. So required to achieve a 10-second delay. So yeah, this would be 10 seconds, then 1.1 R1, and then C, which is this. So again, please show your steps. Oh, and never ever ever do your equals like this. Okay, it's like a general math rule. Don't do this. Don't do this. Very rare you want to do this, but in normal calculations, always do this. Always. Okay. This is not like I'm trying to change your style of math or whatever. Like this is literally like is I don't know, man. Okay. 10 seconds divided by 1.1. Yeah, that works. Okay. So 10 divided by 1.1. 2 again, of course, write out the equation beforehand, convert your prefixes, show the marker how you convert your prefixes. So in the end you get this. Yeah, this is the right answer. Okay. A list of possible resistor values from the E24 series is shown below. Circle the value that most closely matches. Okay, yeah, most closely. So yeah, 4.13 stands around here. So from here to here, what's the interval? From here to here, what's the interval? They didn't ask for you to pick the resistor which is best. They asked you to pick the resistor that is most close to the actual resistance. And because of this, the interval here is higher than the interval here, therefore this is the correct answer. I know why you picked this. It is better to pick a resistor that has, usually it's better to pick a resistor that is higher than the calculated resistance. But in this case, that's not what they asked for. They asked for the value that most closely matches the value that you calculated in the question. Therefore, you don't pick this, you pick this because this is closer. The OR gate in CCTV control circuit is made from 2 NOR gates. Take the correct Boolean algebra. Okay, so this is NOR, so this is correct. And then this is a NOT gate, so yeah. Pin details for 7402 quad 2 input NOR gate. A prototyping board or breadboard is shown in here with this chip already put in. Connect the power supply rails to the correct pins. Oh bro, why'd you do it in green? Can I change the color of this, or like I don't think so. Okay. Okay, 6 marks. For every statement, I'll put a tick if you got it. Connect the power supply rails to the correct pins. For this, you probably only need to connect to VCC. Yeah, so this is probably right. The input A to the correct pin. Okay, for this, you probably need to reference this. So A, you have put it into this. That is this input, I think. So this is correct. The input B is here. So you're connecting it like this into the second input. So this should be right. The two NOR gates together. So because we need another NOT gate, right? We need to use a NOR gate as a NOT gate. And it appears that you have done it like this by connecting the two inputs together. And then you connected the output. Oh yeah, yeah. Okay, yeah, and you connected the output of, oh yeah, you connected the output of the first, you connected this, you connected it like this. So the two NOR gates are together now, and then you connected this as a NOT gate as well, so that's correct. The output Q to the correct pin. So what you did is you connected this to like this, so this is right. All the unused NOR gate inputs to 0 volts. You didn't do this. You didn't do this. Also, they didn't ask you to do this. Also, this, um, I don't know, man. Okay, so you have to connect all the rest of the inputs. So you had to connect this to 0 volts and connect this to yeah, and connect this to 0 volts. But you didn't do that, so you get 5. Not bad, I guess. Figure 12.1 shows the system diagram for an electronic dice. Okay. LEDs are placed in a dice pattern. Complete the following binary table to show the output sequence. Oh, for this is just looking at, okay. So 3, you need this, this, and this. Oh no, this is counting. Oh, okay. Yeah, this is right. Figure 12.4 shows the incomplete circuit diagram for the electronic dice. So a pulse generator, then you can either reset or, okay, wait. I haven't read the question, bro. Suggest a suitable circuit that could be used as a pulse generator. SR latch, funny, bro. Are you serious? Pulse generator, You know what an SR latch does? An SR latch saves 1 bit of data. No way, bro. Bro, okay, astable multi-vibrator. Okay, 555 timer in astable mode. That's a pulse generator. Jeez. Figure 12.4, connect the pulse generator to 74390 counter so that the number sequence can be paused. Okay, this is wrong. This is wrong. Because in this, it's either you count or you reset. But that's not what they're asking. They're asking, make it such that it can be paused. So what's the correct way is probably just not do this. And if you want to do a pull down or whatever, you can, but this is probably good enough. Actually, you're probably not supposed to do a pull down because they don't give. Okay, actually no, it's fine. But basically, this is wrong. So because you connected it like this, that this is wrong. Okay. And you get 0. Take the statement that describes the arrangement of LEDs shown. Common cathode or common anode. This is all common anode though. Okay, this is all common anode because all the wait. It's all common cathode. You know why? Because all the cathodes are connected together. Yeah. All the cathodes are connected together. So this is right, yeah. Draw on figure 12.4 the connections from this counter to the LED array to give the dice sequence as shown in 12.2. Okay, you did not have to ground it, but you did either way. QA. Okay. Okay, so just from looking at QA is fluctuating every single time, and this is always fluctuating. Always fluctuating. So QA should be connected to the center one. So this is right. QB, you've connected it to two LEDs. QB. So, oh yeah, this is right. This is right. Yes, this is good. Okay, QC, you've connected it to the top and bottom. So QC, yeah. Okay, QC. Yeah, this is right. Okay, yeah. Good. Yeah, this is good. The 74390 counter continues to count up to 9, then automatically resets. Using the AND gate provided. Where did he give an AND gate, bro? Okay, my bad. Draw on figure 12.5 the wiring that will make the counter count up to 6, then automatically reset. And then you drew a sad face. Okay, for for 6, it is in binary, it is 1 2 3 4 5 6 is 0 1 1 0. So basically we just want the case when, oh, they give an AND gate. Okay, I see. We want the case when DCBA is equals to 0 1 1 0, and that's all we need. Wait, what? The counter continues count 9 and automate. Oh, count up to 6. Up to 6. That means once it reaches 6, it resets. So what you have to do here is basically they give you a 3 input AND gate. So I'm going to assume this is connected to A, this is connected to B, this is connected to C. And then for A, right, we want to inverse it. Then we connect this to reset. You did not have to do anything else. Okay? It's actually very simple, but you get 0. So when the AND gate was connected, it did not reset as intended, and the circuit continued to count up 9. 3 checks that they could have made. Check the AND gate. Check the counter. Check the pulse generator. Not bad. Okay, first of all, it can't be the counter because it continued counting up. So there's nothing wrong with the counter. It can't be the pulse generator because the fact that it's counting means that the pulse generator is increasing the count by 1. So it can't be this. Check the AND gate. No, it's too vague. You have to specifically tell me what to do. Check how the AND gate is wired to ABCD. Check if the AND gate output is wired to reset. I can only think of 2. I don't know the 3. So I don't know. But yeah, I mean that's not too bad performance, I guess. Section B. Okay, I'm gonna tally up your marks now. So 1 plus 1 plus 2 plus 2 plus 1 plus 3 plus 2 plus 1 plus 2 plus 1 plus 1 plus 1 plus 1 plus 2 plus 2 plus 2 plus 5 plus 3 plus 1 plus 3. So you get 37. That's not bad. So you get 37 out of 60. So plus 31. So you get 68. Hey, not bad. 2 marks to a A2. Alright, that's it, bro. I'm done, bro. This is okay. This is I don't know if I might make another electronics video later. Maybe see how or what you guys want me to do. But this, if not, this is the last video already. This is the last video. So you can watch my goodbye video to for my goodbye lah, because I'm not gonna say anything now. I'm just gonna okay, bye. Yeah, alright.